Okay, so let's look at some example problems with friction, and then we'll be finished with Newton's laws, for now anyway. So we've got problem 35. If the coefficient of friction between a 22 kilogram crate and the floor is 0.30, what horizontal force is required to move the crate at a steady speed across the floor? What horizontal force is required if the coefficient of kinetic friction is 0? So let's draw a free body diagram of a crate on a floor. There's the crate. It's a horizontal floor, so I expect a vertical normal force. I expect the pull of gravity to be straight down. What horizontal force is required to move the crate at a steady speed? So let's say I'm moving it to the right, so I push to the right. I could say F subscript push. And if I'm pushing it to the right and sliding it to the right, then kinetic friction is pushing to the left. If it's moving at a steady speed, then I can expect that the push force is in balance with the friction force. Let's see, I forgot what the notation for the textbook is. We'll just call it F subscript curvy F because I want to be consistent with AP notation. F subscript italicized F for friction. So again, I'm expecting it to stay on the floor, so I expect that the acceleration in the y direction is 0. Since I expect the acceleration in the y direction to be 0, the net force in the y direction is 0. So I can say that the normal force must be equal in magnitude to the pull of gravity. But I've also said that the crate should be moving at constant speed or steady speed. So that means that the acceleration in the x direction is also 0. That is to say, it's moving, but it's not changing its speed. So if the acceleration in the x direction is 0, then the net force in the x direction also needs to be 0. So that says that the push force, the force I push with, should be equal in magnitude to the friction force. That's kind of like my big ideas right here about accelerations and forces. The question is asking us what force is required, so what's the push force to move it? So I'm trying to find the push force. I know the push force is in balance with the friction force. I know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. I know that coefficient is 0.3, so I come over here, here's the normal force, and it needs to be in balance with the pull of gravity. The pull of gravity on the box is equal to its mass times acceleration due to gravity. So that's 22 kilograms times 9.8 meters per second squared. And my calculator is off screen now, but that gives me 215.6 newtons. So I know now that the normal force is 215.6 newtons. I can use that normal force now in the equation for kinetic friction. So the kinetic friction force should be equal to the coefficient of kinetic friction, 0.3, times 215.6 newtons. So 0.3, again, remember, is unitless. And so the force of static friction is 64.68 newtons, right? Unitless times units. And then that tells me that the push force is also 64.68 newtons. Easy peasy. Well, not easy peasy, but it's relatively simple and straightforward. I hope you find that. All right, so now 36. We have a force of 35 newtons required to... Oh, we didn't answer part 2 to this question. Part 2 asks, what horizontal force is required if the force of kinetic friction is 0? If it's already moving and the force of kinetic friction is 0, this is gone. If I push that box with anything other than with anything, it's going to accelerate to the right. So with no friction, if it's already moving, 0 force is required to keep the box moving at a steady speed. There had to be some force to speed it up from 0 meters per second to whatever speed it's going, but once it's going, and there's no friction, zero force is required to keep it moving. That would be Newton's first law. Okay, so back to 36. A force of 35 newtons is required to start a 6-kilogram box moving across a horizontal concrete floor. Okay, so the box moving, that phrase required to start it moving is telling me about the maximum force of static friction. I'm looking at a situation where it's at rest and there's a force applied and there's this like breaking point where it starts to move. So what's the coefficient of static friction between the force and the floor? I mean, between the box and the floor. So here's the box. Again, free body diagram is just a dot. So I'm imagining it a horizontal floor. So that means that the normal force of the floor on the box is straight up and the pull of gravity is straight down. And I'm drawing those two vectors equal, or I'm sure trying to make them equal in magnitude. It might need to be a little bit longer. Like that. Equal length vectors. And then we know that it's 6 kilograms, so we can calculate the magnitude of the pull of gravity. A force of 35 newtons is required to start it moving. So I'm going to again say that you're pushing it to the right. So you push and push, and you push with increasing force. This could be F subscript push to the right until it starts moving. So at this moment, at 35 newtons, you have exceeded or reached the maximum static friction force. So at 35 newtons, it just begins to move. That is telling us that the static friction reaches its max, 35 newtons. Don't forget units. And then we remember that static friction builds in response to some maximum value, and that maximum value occurs at mu sub s times the normal force. I deleted the greater than or less than or equal to sign because we are at that breaking point right now. And this is the only time you can use the equation mu sub s times normal force. Otherwise, the static friction is just whatever it needs to oppose the intent to move. Okay, so 35 newtons is equal to mu sub s times the normal force. Oops, I need to calculate the normal force. The pull of gravity is equal to mg. That's equal to 6 kilograms times 9.8 meters per second squared. That's a dot, period. Okay, so that normal force is 58.8 newtons. And I know that because the pull of gravity and the normal force are in balance with each other. So mu sub s is equal to 35 divided by 58.8 newtons, which is 0.595. We'll stick with 3 sig figs. Okay, so part B. If the 35 Newton force continues, then the box accelerates at 0.6 meters per second squared. What's the coefficient of kinetic friction? I'm going to try to get this all on one screen, but I may not. So this is the static situation. Everything's in balance because it's not accelerating up until that 35 Newton point. Now, when it's moving, it's accelerating. We know it is. It's still on this horizontal surface, and those two vertical forces are still the same size as they were before, and they're still in balance. And we know the quantity of that normal force and pull of gravity is 58.8 newtons. Oh, that's cool. I didn't mean that to happen, but this sort of happens on both situations. Right? This is true for both situations. Now I have 35 newtons. So I made that 4 squares long. I suppose I should make it 4 squares long again. That's your push force. That's still the same length, but now it's kinetic friction. So instead of a 4 square long force, I should have something rather shorter. So this is still the same symbol, F subscript F, but it is now kinetic friction, and kinetic friction is always smaller than static friction. So I know that if that 35 Newton force continues, the box accelerates at 0.6 meters per second squared. So acceleration is 0.6 meters per second squared.